In this video we want to talk about profiling, a topic that has been long suggested and now we are finally ready to talk about. So profiling is basically answering the question, what does my program do, on a very technical level. So the type of profiling that we are going to review is RTS profiling. This uses the runtime system of Haskell in order to get the measurements that we will talk about in a second. But other tools exist, and if you want to have a complete picture of how your program works in conjunction with your operating system, you will need other tools and tools outside of the Haskell toolchain in order to get a better understanding. So, the measurements that we want to take are execution time, memory usage, garbage collection, code coverage, and also multi-core utilization. It's important to note that there are many more. Those are not all of the measurements that you could take, but those are the ones that we will look at in this video. It's important to note that you need to have the profiling libraries installed on your computer. So if you use some package and you do not have the profiling libraries, then you will need to reinstall that package. Also, you need to have the profiling libraries for your base library installed in order to do any profiling. Okay, so let's look at how profiling actually works. Okay, so here we are in an example program where we have a list of ints, and that list gets summed up in F and G. The only difference being that G uses the strict version of fold L. If you're not sure what that strict version actually is, please watch my video on strictness. Something that I said in that video was that the strict version is faster and more memory efficient. So now we want to prove that. Okay, so what does this program actually do? Well, it first fully evaluates XS. This is done so that we have a fair comparison of F and G. If you're not sure what evaluate and force actually do, then watch my video on deepsec. Okay, and then we want to show F and we want to show G. So what happens is we evaluate this lazy list, and then we compute F, and then we compute G. And now we want to profile that. So, how do we do it? Well, we need to compile this program with -prof and -fprof auto as the flags. And if we do that, then we have a new runtime option called -p. And when we run the program with -p, it takes some time. And actually, this time is longer than the actual time that it would take in order to execute this program. This, of course, is because we have some profiling measurements done in the background that also take time. So a profiling program will always take longer and it will allocate more memory than the actual program would. But the profiler is actually excluding all of that from its statistics. Well, but now that might be a good question. Where are the statistics? We have run the program, but we don't have anything. We don't have any summary or something like that. Well, that's because a new file has been created called main.prof. And that is where those statistics are. So, let's look at that file. And here we see some measurements. So, of course, we see the standard information like when the program was run and what flags it had, but also the total time and the total allocated bytes. The important thing is that this is not actually the amount of memory that the program requested from the actual operating system. This wasn't all used. So it's very important that if you need to get a very precise count of how many bytes your program needs, then you should use some external heap allocation analyzer or something like that. Okay, but now we want to look at this part of the file. This is a very, well, those are some very rough statistics on the cost centers. Now the cost centers, when compiling your program with -fprof auto will be all the functions and also constants, like for example f and g. F and g weren't functions, they were thunks pointing to something that needs to be evaluated, that are not inlined. So those functions were not inlined, and that is why they are considered cost centers. And here we have some interesting measures like the time and the amount of allocated bytes that each cost center had. So here we see that 60% of our time was spent in the cost center F. Now this is very important, of course, because if you want to optimize your program, you of course want to optimize the most costly cost center there is. And the very cool thing about this report is that it actually tells you where in the source code you can find this cost center, which is quite neat. So here we also see the amount of allocated bytes, or the percentage of allocated bytes that each cost center had. And we see that 50% of all the memory that we needed was taken by the list itself. And actually another 40% were taken by F. Just 10% were taken by G. So we see that G is much more memory efficient than F. And it is also much more time efficient, as we can see here. Okay, so those are some very basic measurements. So let's look at this. What is this? Well, this is the cost center stack. Every time we enter a cost center, it is thrown on the cost center stack. And this is where Haskell keeps track of those cost centers. Here we have one measurement which might also be very interesting, which is entries. Entries tells us how often we have entered this cost center. Now in this example this is really boring because FG, main and XS were only entered once. But if one of your cost centers is a function that you call a few times, then of course you get the count of how many entries that function actually had, which is quite interesting. Now you might be confused by what CAF means. Well, that's a so-called constant applicative form, which is not that interesting for us. You can think of it as anything like a constant in a program. If you, for example, have a constant like x equals 1 or something, evaluating that, well, also takes time, but of course not much. And that is something that a CAF would be. But we don't really care for that and what it does, because as we can see here, it really doesn't show up in the statistics anyways. We really just care for those cost centers. Okay, so this was a very basic profiling run on this program. Let's look at another example. Okay, so here we are in a bit of a different program, which is a very naive implementation of a sorting algorithm. This sorting algorithm will, if the list is empty or only contains one element, simply return that, and otherwise will find the minimal element of that list called x prime, and then delete it from the list, and the rest of that list we will call xs prime. And then we do a recursive sorting on xs prime. Okay, and here's the recursive definition for the delete function. So if we look at what the main does, we actually try to sort a list going from 1000 to 1. And of course the sorting will be ascending, so basically every element here is in the wrong order. So okay, we need to do some work. So let's do some profiling. Okay, so we will compile it like before. Okay, and we will call this program with the runtime option. Okay, here we've got it, and now we want to look at the profiling report. So if we take a look here, something interesting might come up, which is that we only have 2 cost centers here, which is a bit weird because here we have a lot more. So what's going on here? Well, cost centers that have a, well, percentage of time which is 0 are simply discarded from this summary here, because of course they are not important. Otherwise we would have the whole stack here, but that is sort of, well, irrelevant for us. But this tells us quite a bit. This tells us that the evaluation for x prime in the sort function actually takes more time than deleting from that list, which is quite crazy, because now if we look at the stack, and here we actually see how that stack works, right? Main was calling sort, and sort was calling x prime and xs prime, and xs prime was calling delete, and that is how this whole stack works. But something interesting is that delete was called much more often than x prime was called. Of course, it was only called 999 times, because we had 1,000 entries in sort, and the last entry in sort is the case where the pattern matching finds that the list has only one element, and that's where we simply return the list and we do not do any further computation. So we call this one only 999 times, but it takes more time proportionally than delete does. So if we wanted to optimize this sorting algorithm, we should optimize x prime first. You know what? Let's do that. Let's optimize this, because something that I did here was use the non-strict version of fold L. So let's use the strict version now, but we have to import it, I think. I'm not too sure, but I think we have to. So let's recompile this, and it was recompiling, so let's call it. Okay, and let's look at the profiling data. And now we see that actually, as we can see here, the time difference that it took is now, well, much different. And I think the total time is also actually a bit smaller. So here we could see how we could use this profiling data in order to find the most expensive cost centers that we now could, well, optimize in order to get a better result. So the next thing that I would optimize is probably delete. But then I would find out that this method of writing a sorting algorithm is bad anyways, and you should do it in another way, like for example do merge sort or something like that. Okay, so that's the theory behind profiling cost centers. Now we want to look at memory allocation and how that develops over time. Okay, so here we are back in the fold program that we have seen before. And I will just assume that we have compiled it with the profiling options enabled. What we can do then is we can call this program with the option -h. And -h will give us some information over time how the heap developed. So let's just let this program run. It takes a bit of time. Okay, here we have it. And now we have another file in here called main.hp. Now the problem is that we cannot do much with this file, which is why we need to convert it to something that we can look at. If you have your, well, default GHC installation, you should have a tool called hp2ps. And calling that program on this file will create another file called main.ps. And we're now going to take a look at that file. It's a PostScript file, so you will need to have some viewer that supports PostScript. Okay, so here we are looking at the profile that was generated by hp2ps. So what that file actually tells us is the cost centers that we want to look at for the memory. So G isn't even showing up here, probably because it simply didn't take that much memory, I think. And what we can see here is, well, the amount of memory that we needed for XS and F steadily increases, of course. That is because we want to evaluate the list So we wanted to have a full evaluation, so Haskell needed to create the whole list in memory, and this is the point actually, at this point, so after 0.4 seconds, is the point where f simply didn't need all of the elements of XS anymore, and that is actually where the heap profile, as we can see here, decreases, because elements of that list were discarded because we didn't need them anymore. And this is where we get this decrease here in the amount of heap that we need. Now, this is nice and all, but the problem is that, does it really tell us that much? And to be quite honest, no, it really doesn't tell us that much how the memory behaves. That is a general problem in Haskell, since we are in a lazy language. So it takes a lot of time in order to find out where the most heap usage comes from. Because, of course, a function could build a huge thunk, which then after some time gets evaluated. So you never really know where the actual heap problems are coming from. A rule of thumb is to use, for example, strict versions of certain functions if you have huge data to work on. Because at a certain point, doing lazy evaluation simply needs too much memory. Okay, so speaking of memory, now we want to look at some garbage collection statistics. Okay, so we are back in our folding program once again, and we want to look at some statistics for the garbage collection. Well, you can do that by calling your program with the -s flag. And if you do that, you get this information. Now, if you've seen my last video on parallelism, you already know of most of this information, but I will repeat it shortly here. So, what's happening here? Well, we have some statistics on how many bytes we actually needed. Again, this is not what we needed from the operating system. This is just what was allocated in the heap by Haskell for later usage. But not everything that Haskell is allocating will actually be used. This is the important statistic for us if we really want to look at how much memory we need, because this is the total memory that was in use by our program in our operating system. So this is the amount of memory that we needed in order to evaluate the program, which is quite a lot. Here we see some statistics on the generations of the garbage collector. Of course, the garbage collector doesn't always get active. It gets active in generations. And here we see how many collections it did. In the first collection, it actually, or in the first generation, it actually did quite a lot of collections, but it didn't take that much time like it did in the second generation, where it only did 12 collections. I guess that the collections were simply bigger in this case. Also, a very important measurement is this one, the bytes copied during GC, because the garbage collector has to copy certain data sometimes, and that actually takes quite a lot of time. So keeping this measurement as small as possible is of course important, but not always possible to do in a manual fashion. Okay, and here we have some time statistics. Those time statistics tell us basically how long our initialization of the program took and how long our exit took, which most of the time is simply 0 seconds, but also how long our mutator took, which is our actual code, our actual program, and how long the GC took. Now, of course, we see here that the GC takes much longer than the actual mutator, which is not good, and that is something that is reflected here in the productivity. The productivity is this important measurement that if we want to look at how efficient our program works with the garbage collector, then we should really keep this productivity high. And in the last video on parallelism, we have seen how productivity can actually dip quite a lot if you simply plan your program in a wrong fashion. Also, something very interesting is that if you have profiling compiled in your program, then also it will tell you how much time it took in the profiling itself, which is quite good to know. Okay, so those are some basic statistics on the garbage collection. Again, it is very hard to manually optimize how the garbage collector works. It is much more important to look at lazy values and strict values and trying to optimize that sort of measurement. This is just important to see that if you have a bottleneck in your program, you should know if it is actually the mutator or the garbage collector, because it could very well be that the garbage collector is the reason your program takes so long. And then you need to find some other measures in order to optimize it for whatever you're trying to do. Okay, so now we know how to analyze a bit about the garbage collector. Now we should look at something completely different, which is code coverage. Okay, so here we are in the sorting program like it was before. And now we want to check for code coverage, meaning in the execution of this main, we want to know if every expression in this program actually got executed at some point. So how do we do that? Well, of course we could use print statements everywhere, but that wouldn't be too good. So what we will do is we will compile this program with the flag fhpc. And after doing that, we can observe that there is a new directory in our directory. Here we will find a main.mix file, which we don't really care for. I just want you to be aware that this directory now is there. And now we will execute this program, and it executed, and we didn't use any flags, but nonetheless, we now have a new file here called sort.tix. And now we can use the program hpc in order to report on the code coverage of our sort program. And as we can see here, not all of the expressions that we had were used. We had 38 expressions, but only 36 were used. The Boolean coverage was very good. Well, because we didn't have any guards or qualifiers, we only had if conditions, and well, we only had one, and that was met at some point. And when it comes to alternatives, we only had 5 of 7. So now the question is, this code coverage, of course, if this was a testing our sorting program, this code coverage wouldn't be perfect. So now the question is, well, where did we go wrong? And in order to find that out, you have to call hpc with the markup argument. This will now create HTML files that we will look at right now. Okay, so here we are in my browser, and here we see the HTML files that were created. So let's look at main.hs.html. And as we can see, this really is, if we make it a bit bigger here, this really is just the source code that we had, plus some annotations. For example, we see what was never executed. And that makes perfect sense. It makes perfect sense that we never executed this case and never executed this case, since, of course, we were stopping the sorting algorithm when we only had one element. So yeah, we never executed this one, and so we never executed this one because the list that we wanted to delete from was never empty. So here we see where our code coverage went wrong. If we look at the other files, then we see that this is just a basic statistic per module, how many definitions we used, how many expressions we've used. But of course, for our problem here, we only had one module, so this is not really interesting. Of course, if you had many modules, then this might be more interesting to look at in order to find out if your tests actually covered most of the program. Now, it's also very important that you can find things that are always true or always false. For example, a if false then, of course, will be always false, and thus whatever it points to will never be executed. Here we are in another little example where we can actually see how we could use this code coverage in order to find logical errors in our program.
So here, for example, the guard, the otherwise guard, was used, too early. So those guards were never executed. So of course, the solution to this problem is that otherwise needs to happen as the last case. And then this little fizzbuzz implementation here would be correct. So you can see that code coverage can also help, or HPC can help to, find some errors in the logic of your program. So maybe if you're debugging your program and you just don't know what's happening and you simply don't know where the logical error is, you could use HPC even though it wasn't made for it. Okay, so here we are in a last example. This example is a program we have already seen. It's the one we have seen in the STM episode. So what's happening here? Well, we are spawning threads, and those threads get some number between 1 and 100,000, and they should just add that to some result variable, that result variable being shared between all of those threads. So they basically compute the sum from 1 to 100,000 just in a multi-threaded way. And we now want to analyze how good that actually is and how good our multi-core utilization is for this program. Okay, so we do that with something we have seen in last episode, which is the event log and thread scope. So I won't go too deep into the whole subject. I will just show the basics and then refer to that other video. Okay, so how do we compile it? Well, we have to compile it with the threaded flag, of course, and the event log flag. Okay, now we compile it and now we can run it again with -n in order to use all of the cores I have on my system, which is 4 cores. If you don't really know what that is, then you can watch the video on parallelism or concurrency where I talk about these flags. And the other flag that we will use is ls in order to get the event log. Okay, so let's run that. And the sum was computed pretty quickly. And now we have a new file called stm event log. And now we will call this file with an application called thread scope. Okay, so here we are in thread scope, which is a way of visualizing the event log that we have seen. And more importantly, it is visualizing how good our multi-core utilization is, and especially where the garbage collector takes some time. Okay, so at first we have some general statistics down here, like for example the productivity, which was actually quite alright. We had a quite good productivity, which is nice. And the maximum heap size and stuff like that, which isn't too bad for us and we don't even care. But now we care for this activity graph, because this, the dashed lines, tell us the utilization of our cores. Now remember, I have 4 cores on my system, so Haskell, when executing this program, had 4 execution contexts, HECs. And those execution contexts roughly translate to 1 core on your system. But we see that the actual utilization in the actual algorithm was, well, terrible. It was absolutely horrendous. We didn't have any multi-core utilization whatsoever. We can even, go deeper and we see that, wow, this is horrible. Okay, sometimes it went to the second dashed line, but really, if you look at the average, then it isn't even as good as a single core utilization would be. So what's going on here? Well, the problem we see in those execution contexts here. And we can see that if we look at the key that we have here, we create a lot of threads. This is of course done in this mapping that we have seen where we call fork.io. So one of the threads here is actually doing nothing but creating more and more and more and more threads. And the other ones now can actually do some calculation. But of course, STM is in a certain way blocking. Well, of course it isn't blocking, right? That's the whole point of STM, but still only one thread can work on a resource at once. So basically the whole overhead that we have for more and more management of this resource is the problem that causes us to basically fall below the utilization of one core. And that is the big problem that we have here. All of the threads that are being created have to wait on each other. Or again, STM is not really waiting, but it's a optimistic strategy, but you can think of it as waiting when it comes to the productivity of our cores. And that's basically the whole problem. Now, here we see other problems like the garbage collector at certain points kicking in and causing for a long pause. And that is all, well, that is all a bit of a problem. Now, I've talked about thread scope before in extensive detail in my video on parallelism. So if you care for the analysis of multi-threaded programs, you can watch that video where I also talk about what sparks are. That is something that we haven't talked about in this video, because if you use the parallel library, then you will need to get some profiles on sparks, which again is something that I talked about in my last video. I'd like to close this video with some final thoughts. Now, profiling is nice because in a high-level language like Haskell, we don't always know what is actually happening. So profiling is good in order to understand what our high-level features are doing, especially since Haskell is lazily evaluated. But you shouldn't overdo it and use the data we have seen here in order to, in a sort of way, micromanage your program so that you force some evaluation here and force the evaluation there and maybe defer the evaluation at another point so that you can get the most optimal execution of your program. You really don't have to do that kind of stuff. Optimizations are done by the compiler anyways, because if you compile your program with -0, for example, it is already optimized. And optimizations are something that the Haskell compiler can actually do quite well. For example, the difference between the non-strict and strict versions of fold diminish once you use optimizations, since optimizations, or one optimization in the compiler, is strictness analysis. So just keep that in mind, that when doing profiling, this of course is totally fine and we should profile our programs in order to understand what is going on. But we shouldn't use the data that we've gained from it in order to do some very weird optimizations. It's much better to choose the right algorithm for the problem than to have the wrong algorithm and then just micromanage it into some usable runtime. Okay, so if there are any questions, please feel free to leave them in the comments below. And as always, thanks for watching.
You wouldn't believe how many coffees I run through making one of these videos. If you'd like to support them, you can do so on Ko-fi, where you can, well, buy me a coffee. Any support is greatly appreciated. Thank you.